we have Andy here, and he is doing a new talk.
I should stand up, shouldn't I?
Yes. Feature-orientated exploitation, and I think we're going to be able to play the video game later that he made for this. Is that right?
Oh yeah, there's a leaderboard and everything.
Oh my gosh.
Yeah.
It is not a mermaid game. I have asked. I know we are desperately low on mermaid games. Andy is aware. And maybe next time he will address that. Okay.
If you want to come back again, you bring a mermaid game.
Yes, please.
It's how I'm hearing that.
The tail color and my hair. Anyway.
Oh God.
But I digress.
It's getting ambitious.
So, without further ado, I give you Andy.
Yay! Thank you, one and all. Yes, there is a game to play at the end of this. No, it is not involving mermaids, but it is a crappy 2D scroller game. But there is a leaderboard at the end, and if you get a fastest time on there, I will buy you a pint at the end. I might have signed up to something really bad then if you all get fastest times. I haven't thought this through. So this is the first time I've done a talk inside a pub, and that brings with it interesting scenarios like I have been drinking before the talk, and probably during the talk, and then definitely after the talk as well. So we'll see how that goes long term. The talk is called Feature-Orientated Exploitation, and this title came about through an interesting concept. In the fact that over the last 6 to 12 months, there's been a couple of vulnerabilities that have been disclosed to Microsoft, and they've sort of, their response has been mostly, oh, that's a feature, which was suboptimal in terms of a response. One of them they ended up on backtracking on and releasing a patch for it, which then became a critical patch. Who'd have thought it? But what I decided to do, given all these are termed to be features, is string a couple of these features together into an exploitation chain and see where that lands me, and hopefully not in hot water. And the way we've done that is we've taken some proof of concept code that was released for a cheat a long time ago. I say a long time ago, about a year ago, for a game called Valorant. Anyone played Valorant? A few Valorant players in? Yes. Just fast. Way too fast for me. For mermaid games, I think, for future reference. But we've turned some old proof of concept cheat code for that into something that can also target userland processes and inject into userland processes as well, and extract things from memory that shouldn't really be able to be extracted from memory directly. So, who am I down the bottom there? I'm Andy Swift, obviously, as I've said before. You can follow us on like Twitter and stuff, or whatever you call it these days. I work at 6 Degrees, who have just been acquired by someone, so I don't really know where I work anymore, to be honest. But I am a security researcher, red teamer, pen tester, reverse engineering, incident response, and apparently the CEO of something called SwiftyNet Firewalls, which is a massive parody of Fortinet firewalls for those interested. We have no hardware in the boxes, just toggle switches on the front, endless amounts of fun and infinite security, secure by design. So the glossary of what we're going to do and talk about today. We're going to go through a quick little bit right at the top of just some exploit development jargon, because anyone do exploit development in here on a regular basis? Excellent. I'm glad I put a glossary in, because that's going to confuse the shit out of people otherwise. We're then going to talk about the why the hell I decided to do this, and why game cheat proof of concept code makes such good base for malware and things like that, with writing malware or exploit development code. We're then going to do a bit of a technical deep dive, which, given no one put their hand up just now, this is going to be a mindfuck, but bear with me, and if people get lost, stick your hands up and I'll try and help out where I can and explain things a little bit better. But I've got diagrams and things, so fingers crossed we'll be okay. I'll then talk a little bit about the additions I've made to the proof of concept, just to get it working in things like other userland processes and cause all kinds of absolute chaos outside of games. But this whole thing, exploiting games, is a little bit naughty sometimes. It's a little bit frowned upon. So to get around any kind of legalities of presenting things where I am actively exploiting games in public, I decided to go down a rabbit hole and build my own game for this as well, which is kind of just for you guys to start with here. So you're the first to see this. Congratulations. It's a platform we'll build on over time, and it's going to be, the idea of it is going to be a bit like a damn vulnerable kind of game map, instead of like a DVDL type of thing. So I'll then finish up by talking a little bit about how this works in user land and stuff as well. So as promised, and without further delay, here are some glossary terms for you to remember throughout this presentation. If you can nail these, we're good. So the first one, a hook. Anyone know what a hook is? Yes, I'm not going to quiz you, don't worry. I saw the fear in your eyes go there, like, oh crap, he's coming. So a hook, we essentially think of this as like an event handler. In our terminology here, throughout the whole thing, think of two processes. You've got a attacking process and a victim process. Don't lose sight of that, because I'm not going to complicate it by sticking loads of extra processes in and causing absolute mindfuck. Just two processes, an attacker and a victim. The idea of a hook is that the attacker can then place a hook onto the victim process and await for a particular event to fire. When the event fires, then we want to do something called a callback. Next term, super smooth, segue. So once the hook fires, we want a callback to do something. And the callback is simply a function that we're going to invoke or call once that event handler triggers and once it fires. Gadgets are something we use an awful lot in exploit development. If you've heard of gadgets, essentially gadgets are little bits of reusable code that we might use. They might be buried within other libraries, included within processes. We might bring our own inside DLL files that we just chuck into our process. But the point is, it's a little stub of reusable code. It can be part of a wider library that just does something we want. It might do something as noddy as creating an integer for us, or it might do something more advanced like a trampoline. Funny terms, I know, but the trampoline is a type of gadget that will just jump the execution flow of a process into something else, into another location. So a gadget, first of all, might just write an integer somewhere, and a trampoline might go and execute something to do with that integer somewhere else and change the execution flow of the actual process. You're waving. Is that just to say you're still awake? That's perfect. That's perfect. You do, yeah, you do. You do. Ooh. Thank you. Another sip of beer. It's going to get worse. Messages down the bottom here. So messages. So if you haven't done exploit development on Windows GUI stuff before, there is an interesting concept of messaging between the two, between all different processes. So any process, if it has the same similar type of privileges, can send a message to another process. And it does this via a sort of non-authenticated messaging subsystem. And it can do anything from sending messages on mouse movements or on some kind of shell event, depending on what it is. But the point is, we've got a method of sending messages between processes, usually to communicate things like telemetry or to communicate something like a particular state of a particular process that might be linked to it. Finally, a shatter attack. Now, shatter attacks were kind of coined as a term in 2002 in Black Hat or DEFCON, I can't remember which, but as we are at a DEFCON meet, let's just call it DEFCON. Why not? And it was basically an abuse of this messaging system over and over again. So finding very different ways of taking these messages and using them in sort of nefarious ways to write and read from memory and stuff like that, and escaping sound boxes and escalating privileges. So the ones with a star on, try and remember those ones. If you can't, we'll go through it anyway and we'll get there eventually. So why? It's a big question, but we need to address here. So why are cheats and why is there a big overlap with malware? Well, the first thing is games and applications both sit on top of the Windows API. Of course they do. They both have to run inside Windows, right? So if you pull it apart and you look at them, they're all going to have things like NTDLL loaded. They're going to have things like Shell32 loaded. Both of them will do the exact same things and have many of the same sort of crossover things, crossover libraries involved in both of those. So they also have the same concept with malware and with obviously game cheats. We want to manipulate something, right? So game cheats, we want to manipulate like, oh, that wall there doesn't need to have a texture, and then you have wall hacks. Or, you know, you have more lives than you're meant to, or less lives than you're meant to. We're manipulating some kind of thing in memory. And it's the same with malware. In malware circles, we're taking and trying to extract things from memory. Maybe that's an API key, maybe that's a JWT token, maybe that's some other kind of thing we want to inject into a process to make it do something else. And it's no surprise, but with the same platform and the same concept, a lot of them use the same techniques. Hooks, callbacks, messages, trampolines. It's all common, it's weird terminology, but it's the same sort of common terminology we use in both worlds. They also have the same constraints: stability, noise control, repeatability. You think about stability, first of all, in game cheats. If you're running your nice, lovely wall hack you've just paid for, not that anyone here cheats in games, obviously. Watching the room now, there's a scratch of a head back there. No, but you want stability in that. You don't want to run your wall hack and then all of a sudden the game just quits or had some kind of memory fart where you just can't restart the game or something like that. And it's the same with malware as well. You don't want to be running your malware and then all of a sudden, like, the application that you're injecting into or extracting data from suddenly rage quits in the middle of the user's use case, because then you're going to get burnt straight away. And then the final thing in here is EDR, AV, anti-cheats, they're all doing the same thing, right? I mean, anti-cheat software is looking for a behavior, it's looking for a certain set of instructions or particular function calls, the same thing that EDR tooling is doing when it's looking at behavioral heuristics and things like that as well. So they both have this common crossover where we're trying to evade these things to get around them and find these sort of ingenious ways of doing that. The last point in there is just a point more for you guys. If you want to go out and try this stuff, I'll publish this game afterwards somewhere where you can just get it and just fuck around with it and destroy it if you like. I don't really care. That's what it's designed for. It's designed for people to learn on it. But game cheats are an interesting way of getting yourself into exploit development if you ever want to get in there. Because exploit development can get very boring very quick. And you'll see a bit of that later on when I'm talking through a proof of concept code. It can get very stale. The problem is, though, and the nice thing about cheats is that you've got a very tangible and real kind of thing that comes out of it. If your exploit works, all the walls disappear, or you gain extra lives, or you move super fast somewhere. So it's a very, if you do want to get into it, and you do want something tangible and feely in front of you to look and have that visual feedback straight away, there's a train, then absolutely fantastic. So why treats and the mission? Well, this is what I came up with on Friday, and my Friday afternoon sessions have become somewhat not legendary, I can't call myself legendary, that's bad, but they've become very well known where I work. Thomas will tell you all about my Friday, because it comes up at about 3 or 4 p.m. and I come up with a batshit crazy idea for something. And one of my last ones was, back me up on this, AI-powered tiles for a data center that light up and show you the way to your cage. Eh?
That's really good.
Really good, right?
Yeah.
Thank you. Mixed reactions from the crowd. Hospital wards, there you go.
Your last one was making a phone.
Making a phone was my last one, yes. Yeah. Yeah, that was it. Yeah. Anyway, right, I'm getting sidetracked, but Friday mode activated, and what I ended up doing was I thought it'd be a great idea to acquire some cheat code that had been leaked. And then I was going to, that's a picture of a cheat if no one's ever seen a cheat before, I imagine you have, but for pictorial purposes, the cheat we're actually going to talk about was the one that pinned up this particular cheat, by the way, the framework underneath it anyway. I then thought, well, I'm going to build an amazing game full of holes for people just to poke and learn from over time. And the amazing game looks a bit like this. Hint, it's not an amazing game, it's a 2D scroller with a weird witchy object in it. But fun nonetheless. The idea is to get from start to the end as quickly as possible through a load of jumpy things. That's about it, no mermaids. Then I was going to make some amazing little hacks for this said game as well, to make like you move faster or move slower, and it generally looked like this at the end, and we'll get to that and what that is a bit later on, but it worked eventually. And then what I thought would be a great idea is to use that same code to target other Windows applications. So things like browsers, things like password managers, things like Steam, things like the NVIDIA overlay that sits on top, and just injecting into stuff and seeing where the hell it goes and what's in memory there. So to do that, I needed to expand the interface to go hunting for targets rather than just focusing on the game. So all of this is coming, and it's all quite interesting. And there's a sample of some of the stuff we got out of certain applications, which I'll talk about later. Literally OAuth tokens that it can pull out just by sitting by the side of it. That was pulling it out from a sandbox application, by the way. Just might give you some clues about what it is. So Christmas time came around, which wasn't actually Christmas, it was a month early, but nonetheless 25th of November rolled around and the UC forums literally erupted with news of this new leaked code that had been put out there. And UC, for those that don't know, is unknowncheats.com or .me. There's various dark web locations for it as well, but a place to share and talk about cheat code and things. But this guy here self-published this as well. He self-published his proof of concept code because somebody before him had leaked it. And he was so disappointed with the manner that it had been leaked in and the way that the person that leaked it had explained it to people that he decided he was going to leak it himself and do an actual better explanation of what was actually happening under the hood. There's still a lot to find out and there's still a lot to reverse engineer, but long story short, it's a zero-day shatter attack that at the time bypassed literally every anti-cheat tool on the market. It was used heavily in Valorant cheats, for ESP-style cheats and wallhack cheats as well. Now, in terms of money is always like the fun thing to talk about with exploits, right? Because like, who sold it to who's on what bug bounty programs. But Microsoft decided that they weren't going to class this as a bug. They were going to class this as a feature, and they weren't going to fix it. So no bounty was paid out to him via the Microsoft disclosure route. But what happened is he went and then sold it privately for upwards of a six-figure sum to give you an idea of how much these people paid for it. And that private company then took it and then built their cheat code on top of that, because this is essentially a framework that he's built to build cheats on, or a technique to build cheats on. So a day later, Christmas number 2 came around on the 26th, and he released it on GitHub as well. And the GitHub repo looks a bit like this. You can go and find this today if you really want to try your own hand at this as well. I recommend you do if you really want. Or this one just contains a README file that has this in it. So there's not much description about how it works or what happens. So you might want to go, and I will make a point of releasing my one after this, because what I've done is I've made a README file with literally line after line of what it does inside it, and I've made pictures and diagrams and also this presentation as well. So I'll give you guys all about it if anyone's interested in reading about how this works and you want to take it and modify it yourselves. So I did what any other good pen tester would do after that with random code they've just found on the internet. I compiled it without any care in the world. If you're any pen testers in the room, yeah, don't do that. Especially you, because you work for me. So if you're compiling randoms, especially if you found it on his GitHub page. So we decided to compile the code. The code's mostly a framework. Out of the box, it literally does nothing if you run it, because it doesn't have a target. It doesn't know what you want to do with the code. We haven't plugged anything into it. So I thought I'd just hard code a little target in there, and I hard coded it to look at the classic notepad, just to see what it could open up and what it can do. This I'm now realizing is very small for you guys to see over there, so you might have to squint, move closer, or use your imagination. But all of the detail in here, you can see it's just firing up the exploit targeting notepad.exe and then doing some interesting things. So once it's compiled and once it's running, what the fuck just happened was the question that I put to myself, because the key here is that even with this output up here, you see there are references to things like set Windows hooks. So we know we are hooking other processes. And then there is this curious thing here, shared memory. What does that even mean? How is it using shared memory? And where does that exist? What's it using it for? And what clever way is it using that to evade anti-cheats and detections? So the other thing that was missing was the usual suspects. So AV and EDR tools commonly look for things like read-write process memory, or things like virtual alloc, just because virtual allocations of memory or injecting and writing processes into other memory, into other processes, is kind of frowned upon and is sort of seen most of the time as a bad thing. So it's a fair sort of way to light up a Christmas tree if you do include these in your malware. Most malware goes down the route of finding clever ways to hide the fact that they are running these kind of functions and injecting into memory. And that's mostly the route they're taking, but there's no reference to these in the source code at all if you grep over it or you search it. So again, what the fuck is happening? How are they doing this? The other thing that piqued my interest is I forgot to turn off Defender for Endpoint when running it. Now, Defender for Endpoint in my environment is hooked up to a lab environment in Sentinel, which are SOC monitor. So not turning it off was a bit of a fuck up, but the best thing that came out of this is that No alerts were generated during this, this exploitation chain. None at all. It didn't stop us. It just ran in the background and did its own thing. No alerts even in Sentinel, no trail of it even happening. Because all the things that are using underneath, it's leveraging Windows hooks, shell event lookups, and it's using the standard messaging system as well in a kind of legit way. So it doesn't really sense anything is particularly wrong here. And that's the beauty of this whole exploit chain. There's no additives as well, so there's no abuse of code. We're not injecting our own things. We're just using mainly NTDLL and Shell32 and stubs of code within those to abuse the processes, rather than bringing our own stuff to the party, bringing our own malware, bringing our own DLL files, our own C2 or anything like that. So there's nothing really for it to trip up on, in theory. So now we get to the fun part. I say the fun part. This is the part where everyone's probably going to look very confused at me for a vast amount of time, I would imagine. But I will try and make this make sense. So picture those two processes once again. We have our attacking process and we have our victim process. We have this space in the middle of them, and in between all GUI processes within Windows, by the way, we have this shared memory space called Windows Shell Global Counters, and that sits as a shared area of memory, a physical set of memory pages that sits between a number of different processes within Windows. Literally every GUI process you have will have access to this shared location. Now, the real fucker with this is that every single process will have its own address for that particular shared memory location. So each process has its own virtual addressing, so it knows where that is. The trouble is, if you're the attacking process and you're attacking a victim process, you want to know what the victim's virtual addressing is. Otherwise, you can't really do anything with it or tell it what to do. So this is problem number one. And this is where we bring in something called probing. Sentinel probing. So Sentinel probing is a way of just understanding what that virtual addressing is. So what we're going to do first of all is we're going to install a hook on the victim process from our attacking process. That hook is going to search for a very specific thing. It's going to search for shell events. So whenever that hook sees a shell event, it's going to fire. And when it fires, it's going to do a callback, and it's going to do a callback to this function here within NTDLL. It's called RTL get integer atom. And all that does, it's mainly undocumented, which is thanks Microsoft. But all that does is creates a Sentinel value for us. So in other terms, it creates an integer or it creates a random number. That's all it does. That's all we're using that little bit of function to do, is create a number. And then once we have that number, we're going to write it into that shared address space if the next bit, the trigger, is actually correct. So we're going to trigger this hook by sending a message. So do you remember that messaging between processes we talked about right at the beginning? So we'll send a message to our target process with this app command parameter in it. And when we send it with that app command parameter, it's going to immediately trigger a shell event, which is what we want to do. So if we send that message, we're going to trigger the hook, and then we're going to trigger the callback to create us a random integer. With me so far? Sort of. Okay, good. Also within this trigger, we have space to provide a parameter for a memory location or a candidate memory location. And the key thing to understand about this, and by the way, if you understand all of this, you understand all of it. We're going to rinse and repeat this and just do it in a loop over and over again. So the message here in the trigger is going to contain a random brute forced memory location, one after the other. It's going to trigger this hook, it's going to do the callback, and then write an integer to shared memory if that location is the correct location for shared memory. Making sense? So we go around and round and round in a circle. We try millions and millions of different iterations of, is it at this location? Is it at this location? Is it this location? And if it is, it's going to write a number, an integer, into shared memory. And all we have to do as our attacking process is monitor for when that number appears in shared memory. I have a diagram to make this somewhat easier to understand because it is a mindfuck. I get that. You have your attacker process on the left-hand side here, your GUI process on the right-hand side here, and the physical memory pages in the middle there, which are just locations any process can write to. we have our own virtual address for what this points to in our attacker, and in our target process, it has its own virtual address down here for where that maps to. So we then set our hook on the GUI process, we wait for the hook to fire, and we're going to trigger it to fire by sending a message from here to here. When that fires, it writes an integer into memory and into the shared space down there. We then monitor here for looking for that number that we've just said is there, and if it matches, great, we know that is the address, because that's the address we sent in our message the first time round to try. Right? Pretty easy, right? Pretty easy, pretty straightforward. Breeze. Stage 2. so that is the be-all and end-all of the main exploit. It is essentially just keeping that concept of the two processes. We're using hooks and triggers to write things in and out of shared memory, and that shared memory is our conduit for taking information out and in of that second process. So what we're going to do, just writing numbers into memory is kind of boring. We need to do it because we need to understand the location, the virtual addressing for that shared memory on our target process. So what we're going to do now is create something called a dispatch struct. So anyone familiar with structs? It's going to be a bumpy ride. So if you think of a struct, like a delivery driver and I'm making this up by the way, a delivery driver and a courier company. So every delivery driver needs to have kind of 3 or 4 things, I suppose. They need to know the address they're taking, and they need to know where they're going, and who they're delivering it to and what the package is, right? So they need to learn a series of information. That series of information doesn't change depending on their parcel. They need to know that information to deliver the parcel. So same in programming, where we create structs of information that's reusable. So reusable types of information. It might be a pointer, it might be a set of arguments, of parameters. The point is we create a structure that can be used over and over again in a loop. And we store that at memory location 0x800 in the shared memory space. And what that struct looks like in coding terms, Dan will tell you all about these from his GitHub repos, all the structs and everything from coding. So our struct here, it's commented as well, I put comments in. So you've got here a function to execute, a function arguments, a location of our trampoline, a number of other buffers and sources and destinations and parameters and variables to pass over. And this structure is fairly static, but we're going to load it with different functions and different arguments depending on what we want to do. We might want to read from memory, we might want to write to memory. But the point is, this is a reusable structure that we can use over and over again, and we store in memory. We use our hook once again for set Windows hook. We use it with the W shell again to, on a shell event, create the hook and fire the event. But this time, we're going to use gadgets instead. Instead of just our message to create an integer, we're going to use 2 gadgets. The first gadget is found within inside NTDLL, the second gadget within shell32. The first gadget, all it does is it finds the location of this struct and loads it into the process, the victim process. The second gadget is called a trampoline. You can guess what that does, probably, maybe, if I've been speaking correctly, maybe. It will execute what's in the structure. So one is to find the structure and load it, the other one is to execute it and change the execution flow of the actual process. So 2 gadgets. They're found like this, which is rather crude within memory for programmers in the room. It's literally using a regex pattern to find in memory the location within NTDLL's library, this particular function that the developer wants to find. And it might not be an entire function, it might be a small stub of code that just handles a specific thing, but he's bound this to W. What this bit of code does and what this gadget does once it is found, this gadget just brings up the dispatch struct, loads it into memory ready for use. That's all it does. The trampoline down here, similar concept, there's a regex to find in memory that particular bit of stub of code that he's looking for, and then he then uses that rather crudely, assigns it to variable t for trampoline, and away he goes. So small little stubs of reusable code that we can use. Legitimate, they're inside shell32 and inside NTDLL. So they're legitimate pieces of code, we're just reusing them for our nefarious purposes. So after we've got the gadgets done, the same thing happens again, really. We send a message over to trigger the event, and once the event triggers, it's going to run the callback, and it's going to run what we use and what we put inside our message. And inside the message, I don't know if you can see this down here, but there's a reference to the memory location down there that our struct is hosted in. So we're just telling it to run the struct, basically. So in diagram terms, once again, pretty diagrams. The attacking process looks very much like this. We have the structure built here, we have a function which is a target function we want to run, and a bunch of parameters and arguments, but we don't need to but we don't need to pay attention to these too much right now, to be honest. We'll get to those later on. The key point to understand here is we set the hook once again. The callback is this ntdllw function, which is the calling our dispatch struct. So we're loading this up into our target process over here. We're hooking it, we're running it, and then we are jumping to it to actually execute it as well. And all of this execution happens just because we've put our little struct inside the shared memory, and we've told the process to go get the struct and then run it. Kind of makes sense? Sort of makes sense. Cunning so far, right? Very cunning. Stage 3. I promise this is the last stage before people's brains melt and fall out. This is where we get to something called read, write, and primitives. So we're going to use this to actually read and write things from memory at this stage. So our code doesn't do this by default. It doesn't do it now. It doesn't read anything from memory. All it does is load a dispatch structure inside of memory and does whatever the function inside that structure tells it to do. So the function we're going to put inside our structure now is called RTL copy string. And this structure, we're going to use it to basically copy data from one location to another. It takes two parameters. It takes a source and a destination. So it takes a parameter of, you want to copy data from source? Yes, okay, well, I will put it in destination. Simple, right? That's all that does. Super easy, super easy. That's all it does, all it does. So when the hook fires by us sending our message once again, any data that is at the target address that we give RTL copy string is going to be copied back into the shared space. And that's a key point to understand about this whole exploit, is we are getting it to copy some stuff from itself into the shared space. Whatever memory we tell it to copy, it's going to dump it into shared space, and then we're going to read it as the attacker. Kind of cool, right? The same process happens for writing, it just works in reverse. So we put something in shared memory space first, and then we tell the target process to go and get what's in shared memory and execute it and do whatever we want it to do from there. So same thing, but in reverse. Diagrams, once again, to keep everyone happy with diagrams, it kind of looks like, we'll get to the game in a minute, I promise. We have our command structure once again. So we set up our struct once again. This time you'll notice in here, if you can see, instead of just a blank canvas, what we've got in here is RTL copy string as a function to execute. We dump that structure inside memory here, in this bit of memory here. We then set our hook over here, send it a message to go and get that crap from memory, load it into here, run it, and then what it's going to do, the dispatch struct is going to run the RTL copy string from the source and the destination we've given it, copy whatever we've told it to copy, and then use the trampoline to dump it back into shared memory space. So we've got a fairly advanced copy and paste kind of mechanism going on here, where it just copies whatever it tells it and pastes it back into shared memory for us to pick up at a later date. So the use of shared memory space is literal genius, and I love this concept because we're not injecting into anything. And if you think about browsers, right? How sandboxed are browsers these days? Pretty, right? Do you think this affects browser sandboxing? Or do you think it dances around it, given what you've listened to? Because what we're causing it to do is the target process is doing all the heavy lifting for us. It's literally copying bits of itself from within the sandbox into a shared memory space, rather than the other way around of injecting and trying pulling stuff out of the sandbox by various fancy ways. It's just using the process's natural behaviors and messaging systems against itself. The reuse in this is also brilliant as well. He's used to things like routines and gadgets that are loaded. We're not bringing our own binaries, we're not loading our own gadgets, we're just using things from 2 DLL files that are loaded into literally every process within Windows. And the best bit of it all is Microsoft sees this all as legitimate functionality. Ta-da! And I don't think they can fix it, to be fair to them, because fixing it would include a massive overhaul of a whole sort of messaging subsystem between processes on literally how the GUI works in Windows. And I don't know if that is within their scope to be wanting to go and do that for what is a fairly sort of small use case here. So think of this then as a kind of framework. It's a basic method of getting information in and out of a process that we don't usually have control of, or a process that we are adjacent to. So say we've just launched some malware and this is our malware, and you want to pull a load of data out of a browser, for example, this is the use case for this. We want to also go hunting, but we also want to, in our game, have some fun first, and we want to look at things like variables. We want to be able to hook variables in memory that are stored on clients. Anyone done game development before? Yeah? What have you used? Any frameworks? Or? Nice. Okay, awesome. Well, you'll know for a fact then that anything you put client side is going to be kind of fair game. And if you're doing especially multiplayer games, the server side has to always have control over literally everything. It's the sole source of the truth. So in this particularly poorly developed game I've made here, everything is on the client side and not verified by the server because I want it to be shit. But we have in here a concept of lives and health and things like that for us to run. And we want to use our cheat code as a method of targeting a very specified GUI window, i.e. the game. So we want to give it that as well. We also want a method to be able to enumerate things within the game, so enumerate things like variables, interesting things to mess around with within the game to cause various effects. So is there a variable called lives? Is there a variable called health that we can affect? Where does that sit in memory, and can we affect it and change it? So time for some observation, people. I'm going to put a game on the screen now. Now I've just confused the crap out of everyone talking about shatter attacks. I'm going to sit down here, so just sort of, you can just imagine me standing up there if you want. I don't know. I'm going to have a sip of beer whilst this loads up. There we go, it's loaded up. So I'm going to enter the name as just DEFCON. And this is sorry, I couldn't remember what number you were after. But, I think, can you? No. Aha! So all this game is a simple side-scrolling game like this. It's made in Unreal Engine. You can see at the top right-hand side, you've got a timer that's now started because I've run through the portal, and you've got a number of lives as well, and you've got this crazy little witch person as well. The idea is very simple within this game, and it is to get from one end of a map to the other end of the map without killing yourself or falling off stuff. If you do fall and stuff like this, you can die, you do end up just back at the end, lives decrement. You can get to the end of it if you really try. I'm not going to do that live unless I do like a speed run here with some kind of miraculous ability. But it does, oh fuck it, I've died again. Whatever, you can see how frustrating this is. But we've got a number of things to play with here. We've got times we can manipulate, lives we can manipulate, speed that we can do, because speed's obviously a big factor. If you do get to the end, it stops the timer and puts you into a leaderboard. So at the end of this, feel free to come up, try your hand. If you top the leaderboard or get a fastest time, I will buy you a beer. I'll buy you 2 beers. No, actually, no, because I've written the cheats here for you. So that's cheating the cheating. But yeah, so in terms of the cheat code I've written, I've used, as I was showing Dan earlier, the actual sheet itself got a bit large in terms of the pages and all of the options I was putting into it. So yeah, I did use AI to make like a little interface at the beginning of it to wrap everything, because it's just so much easier. So look, hopefully this works. Live demos, and you're never meant to do live demos in cybersecurity, but I thought, fuck it, there's no other way I can actually tell you to do this. So I've built it in so you can browse for a target and select a target. Our target is the Unreal game running here at number 2. So if we select number 2, it will then do all of this fancy stuff up here. And I've tried to comment literally every line in code that I can to be as verbose as I can. So if you guys want to pick this up again at some point and you want to run this code yourself, you can see everything I've spoken about in the presentation and that's in the diagrams as well here running. So you can see here we're loading system modules. We've got a named section. We've worked out where that is locally, so our local address space for that shared memory location. You can see in here we're doing some We're doing some hooking down here, so the location of our hook gadget within NTDLL. You can see our trampoline gadgets as well, and you can see it actually working in the background. And I've tried to comment literally everything I can if people want to learn from it. There's also some funky stuff with memory protection down here that it does, but I thought that would be, that's another slide for another time. I've hidden it. It is there if anyone wants to come see it at the end about how memory protection works in this. It's another genius way he's doing it, but it's just, the scope was just getting too big for fit in the presentation. So with that said, we're now hooked. We know the location of our shared memory. So now it's time to start grabbing things from shared memory and sticking there. So I built a little Unreal toolkit in here as well. So we can literally scan all of memory for the max walking speed of our character. So that's what it's kind of doing now. And I'm gonna pause and have a little drink of beer here whilst this works. Hopefully it won't take too long, but you can see all the other variables that it's finding, things like braking friction factors and stuff like that. So these are all editable things we can find. There's like friction factors for the ground, gravity and stuff like that we can edit as well. And because all of this is stored client side, we've got access to it in memory, which is quite helpful, because for our exploit, that means we can literally tinker with and patch literally any of these values that are coming up on the screen. So you see here it's now completed. We've got 79 references to the walking speed. So this is where it gets a little bit janky in my code, because I don't know exactly which one of the 79 the walking speed actually is. So this could be fun. So I built this other little function that just automatically patches all of them in the hope that they are all walking speed and none of them are actually something important that we're about to overwrite with a value. So we'll rewrite that with, give me a number. 7,000. Fuck me, I've never tried 7,000. You only live once. So I meant to do an epilepsy check before that, in case anyone was, because it does flash an awful lot. But assuming no one has dropped dead in the audience, that is, 7,000 has crashed it.
You didn't specify the number.
Yeah, there's probably a reason why I haven't used 7,000 before, to be perfectly honest. So let's just quickly get us back to where we were and see if something less than 7,000 actually works. Yeah, someone said that once. Absolute bollocks, to be honest. So yeah, oh God, we're going to have to scan for it again, aren't we? Yeah.
Is there a way to kind of force the value of the victim process in the temporary memory, or do you always have to scan for it?
Got to scan to know where it is.
Yeah, but could you not like manufacture where it is in the memory?
Once you know where it is, yes. Oh, you mean from the game development perspective? No, not really.
No, from like, you know, so just, I mean, it doesn't take very long, but,
No. Oh,
you know,
yeah.
rather than enumerate it, could you force it to be in a specific place?
Oh, I see what you mean. No, once the game's running and it's in memory, it's kind of fixed location within memory. There are multiple targets for it as the game runs, but yeah, it's a bit hard to do. Once you do know it though, the first scan through, you know where the location is of subsequent runs. So you don't have to scan and just patch all of the 79 candidates that I've picked up. You can do it in a little bit more elegant way and just patch one of them, for example. There's an option in here to just patch one of them, just a manual patch of one if you know the exact location of it. But that requires you to enumerate first of all. So yeah, we'll go for it again. If it crashes again, then I'm very sorry. But let's just set it to 100 this time. It's crashed again, hasn't it? No, it's back. We're back. We're good. So the default in Unreal Engine is 600 for things. So this should move very slowly. So there you can see the cheat is working, it's injecting. We can also change it to be something ridiculously large. Again, as you mentioned, 7,000 again. We're going to go for 7,000 again, are we?
No.
I'll go for 1,000. I'll be a little bit more conservative. Yeah, stress test. And you can see now we're running super fast and we are now lagging as well. So look, I'll come out of the game and we'll get back to, there's another train. I won't get used to that.
Sorry, I should have warned you.
Yeah. So there you go, a cheat for a game. Ta-da! I don't want to applaud that. It's terrible. Right, okay, so cheat is forever. Good, done that bit, success, working. Cheats, working. I want more. There's your mermaid. I didn't realise I didn't do it on purpose either. But the cheat code works as a proof of concept. It works as well. So we're literally reading the values of the walk speed in from memory, altering it, and then writing it back in again out the other side using that technique that we've just described throughout the presentation. But I didn't want to just leave it at game cheats because that's boring. I wanted to affect some stuff inside browsers. And games are not the only kind of GUI thing that happens within Windows, right? We've got browsers, we've got password managers, we've got all sorts of goodies that sit around there. So if only there were a candidate among us that just stored sensitive data in plain text inside memory. If only. So late April 2026. This is the second feature. And people might remember this one because it hit the headlines quite hard about the Edge browser storing and unloading all of its password manager details into plain text in memory at startup. No authentication, no nothing, no PIN numbers. Literally just opening the browser would cause all the password manager credentials to be dumped into memory in plain text. It wasn't even difficult to exploit. Someone wrote a fancy script for it, but as a proof of concept. That worked really well. But you can equally just Control-Alt-Delete on your system, right-click on the process, Edge, and dump its memory. And then you can use the hex editor just to search for all of your passwords. And lo and behold, they will be there, which is scary as shit, right? They did patch this. They patched this about a few weeks ago, I think, which is great because I was like, haha, I can do this talk on it. And then like now I've got to the talk, it has actually been patched. But they patched it as a critical vulnerability, which is a vast kind of departure from where they were claiming it was as a feature many months ago. By design, they said, which resulted in the usual sort of backlash from the security community, which just took a battering stick to it, to be honest. So yes, there's even more to this story as well, because something that people didn't really realise at the time, because everyone was hating on Windows and Microsoft Edge, as is tradition within our community, everyone sort of forgot about Chrome and Brave and all the other Chromium-based browsers and how they handle passwords. Now, they don't handle passwords in the same dumb as shit way that Edge does, admittedly, but in Chrome and in other Chromium-based browsers, some of them, Chrome in particular, does load passwords into plain text memory, but it does it only if you have the password manager open. So if you have, and by that I don't mean clicking on it to open up passwords or view them or putting your password in to view the passwords. So if you do that in the password manager through the GUI, it will ask you for a PIN or a password to do that. But if you have the tab open for the password manager, it will still load all of your crap into memory one way or another. Still a problem. So they don't escape this. But this gives us a really nice target for our exploit, right? We know it's storing stuff in plain text in memory, and think about all the other goodies within browsers as well. JWT tokens, session cookies, yada, yada, yada. It's all there, passwords. So they make really nice targets. So we're going to target some browsers with this basically as well. And there's that question again about sandboxing and does the sandboxing matter? In this instance, not really, it doesn't really matter because we're getting the process to do all the heavy lifting for us. So once again, and for the final time today, observe. I feel like a weird magician. Weird is definitely the interesting word to use. So I'm going to shortcut some of this a little bit because it will get fairly tedious otherwise. But if I've got Google Chrome here, and I have Google Chrome here for the reasons of opening up. I've removed all of my accounts for it, so that shouldn't screw anything up. I'm going to open the password manager, just so it is open in the background, and I'm just going to leave it sat there. You'll notice that if I actually want to view any of these, like this test one, it's going to ask me for a PIN straight away, right? But it is just sat there for now, and I'm going to leave it sat there. So what we'll do with the exploit is use the browser plugin now to select the particular window. We'll select Chrome from the list. You'll see it flashing a few times because we're interacting with the GUI, sending messages to and fro, hooking the crap out of it over and over again. And then the next thing we're going to do, and hopefully this won't crash the browser as well, is we're going to scan for things like auth tokens. It's crashed the browser. So as you can realize, this is incredibly reliable. 10 out of 10. Actually, oh no, I might have been a bit premature there. I might have been premature. Hold on. Let's go back again and rerun it again. Sometimes it disappears from the GUI altogether, but it's still running in the background. Go figure. Sorry, back. Need to work out how to use my own tool, right? It'd be a good idea. So there we go. We've got our hook on it. We'll do the auth scan again, and scan for. Yeah, let's just scan for those again. Wait. I think it might come back to life. I think it might come back to life. Give it a minute. If it doesn't work, I'm just going to go straight to playing games. I think. There we go. I told you it would come back to life. So these are all JWT tokens for various sessions I've got running. So the sessions that are running in the background here, it's linked up to Pastebin, so it has session cookies for things like Pastebin in the background. So if you do want and you want to steal a JWT auth token, have at it. It's for a test account. It doesn't matter to me. But it is pulling things like session cookies and auth tokens straight out of a browser process. And it's not even getting choked up by the sandbox or anything like that. It's not putting up any blockers. It's just sort of happening, which is kind of cool, right? Kind of cool. Thank you. Very cool. Yeah, I know. And just to demonstrate the other problem with this as well. And again, I hope this will work too, is within Google Chrome, you've got all these different processes running, right? It forks itself down into a million different pieces these days, which is incredibly annoying. But you can, if you are interested, go and do this at home as well. You can just create a memory dump file like that of a particular process. You can open the file location and then you can go and dump it into a hex editor. And when you dump it into a hex editor, there's a kind of chance that you might find something related to a password in there at some stage in time. You will need to search for it, obviously, and I can't remember for the life of me the password, but let's just hope I called it something like that, maybe temp123, and you find different use cases of it all within memory. There we go. Actually, there you go. So you can see down here, just through searching through that hex dump, we've got reference to the username, which is temp123, and we've got this is a password, temp123, which is the actual password I used on the fake account. So again, I haven't authenticated to Chrome. All I've done is open the password manager. And there are other passwords in here that I can't remember, but there's just that one being there. That's from the Pastebin account. If you want to log on to my fake Pastebin, crack on. But that's from the Pastebin account that I've got saved in there. That's all it is. So yeah, a lot of danger and a lot of interesting things happening as we go along there. And that exploit is very, very, very useful. So let's finish up then, and I'll give you guys back your evening, let you get back to drinks and stuff. As you can see, I kind of got sidetracked and went down a rabbit hole and didn't put any links in here. But what I will do is I will send the links around at some other point in time, and you can get hold of the game I haven't technically published yet. You're the first test run of this tonight, by the way, if you want to fuck around with it after this and earn yourself a pint for winning the high score. But once that is done, I'll put a link up. I'll post it on the Discord channel for you guys to just mess around with, download, and do what you like with. I'll post a link to my GitHub page with my proof of concept in it, but includes all the README files with descriptions of how each stage of this works and all of the diagrams that are seen in this presentation as well. So you can, if you want to, get to grips with it. If some of this confuses the absolute crap out of you and you want to talk about it, not from a therapy point of view, but from a kind of I will help you along with it understanding point of view, give me a shout on Discord. I'm on there posting stuff sometimes. So yes, give me a shout there. Just as a closing thought as well, please come up and play, ask questions, have a beer. If you want to know more about things like the memory read writes and stuff like that, do ask questions. And look, thanks for entertaining me and my presence here. Thanks for bringing me a weird dinosaur thing that you've printed at home. I'll show this to. Is this going to be explicit on YouTube? We don't know. We have no idea. But he's printed me this lovely dinosaur with a.
There's a story behind it.
I don't think.
Once when I sell them.
I don't think this needs a story, but the CEO of DinoDix.com is sat right here. If you too want yourself one of these bad boys,
All colours available.
all colours available, then do ask. Cheap, reasonable prices.
Yes.
But yes, yeah, thanks everyone for listening. I know it's been a long one. I know there's been a lot of, it's hot up here as well. And I know there's been a lot of learning and a lot of like brain busting stuff on there. So yeah, any questions, come shout, but thank you.
So much.